Welcome back. So this is my second part of the Specialist Math Exam 2 solutions to this year. Right, so let's have a look. Question 1, 12 marks. A particle moves in the xy plane such that its position in terms of x and y meters at t second is given by the parametric equations x equal to 2 sine 2t and y equal to 3 cosine t, where t is greater than or equal to 0. Okay, so firstly, we want to realize the equivalent form for this particle can be written as that, which is a vector function. So our key to tackle this problem is to define x, y, and also our position vector r of t. Here comes my solutions. On my TIN SPY, I just define x1 as x, y1 to represent y, and my position vector consists of xi and yj, okay? But to define the position vector in your CAS calculator, you need to use the row vector or sometimes column vector. So the first part of the question wants us to find the distance from the origin at time t equals pi on 6. What you should write is r of pi on 6 equal to square root of 3i plus 3 root 3 on 2j. Then you want to find the difference between the current position vector and your relative position vector, the relative point. So r pi on 6 minus 0 vector, take the magnitude, will give you the distance from the current position to the origin, which is square root of 39 on 2, okay? Very easy. The second part, let's have a look. We want to express dy dx in terms of t. Okay, so you need to address that part. And hence, find the equation of the tangent to the path of the particle at t equals pi seconds. Equation of the tangent to the path of the particle at t equals pi seconds. Right. So let's say, because I already defined my y1 and x1, so we can get dy dt dx dt. What I should write here is dy dx from chain rule is given by dy dt over dx dt. And directly from our CAS calculator, I can get minus 3 sine t over 4 cosine 2t, okay? Then I need to substitute the t value to get my gradient value. So I just write dy dx at t equals pi. The number is easy, 0. Finally, this line here on my CAS operation is to find my equation of tangent. Now you can see why at the beginning I defined this one as y1 and x1, because x and y, these two letters are commonly used. I don't want to see any variable clashes. If I define the functions as x and y at the beginning, these two will not be able to be used, okay? So here is my step. Y minus y of pi. Let's say y1 of pi is the gradient times x minus x1 of pi, which means I got y plus 3 equals to 0, therefore it is just a horizontal line, y equals minus 3, okay? Easy. The second part of the question, I want to find the velocity. Here it is. Find the velocity v in meters per second of the particle when t equals pi. So On my CAS calculator, I directly differentiated the r of t I defined before, and I got v of t is just first derivative of position vector 4 cosine 2t I minus 3 sine tj, okay? And then I want to find the specific velocity by substituting t equals pi, which means I can just write it as 4i plus 0j, or you could omit plus 0j because it doesn't exist. You can just write 4i, okay? Easy. Next part, we want to find the magnitude of the acceleration at t equals pi. So I took the second derivative of position vector, which means this is just my acceleration vector function of time. So acceleration is the double time derivative of r with respect to t. And I should get this expression here. So when t equals to pi, I directly get 0i plus 3j, and the unit is in meters per squared second. But we want the magnitude, not just a vector quantity, which means I should take the square root of 0 squared plus 3 squared, and I should get 3 meters per squared second. This is how handy our CAS calculators could be. So make sure you realize this little button here, this little command, norm. Norm means you are finding the length of a specific vector or finding the magnitude of a matrix, okay? The next part. Find the time in seconds when the particle first passes through the origin, which means x is 0, y is 0, 2. On my calculator, because I defined x1 and y1 before, I just equate them to 0 at the same time. Then you could give just an appropriate domain restriction. So we start from 0. And one thing I really want to mention is the function. Let's have a look. These two functions. This one has period 2 pi over 2, okay, which is pi. This curve here, p of y, the period of y is just 2 pi over 1, which is 2 pi. But which one should I choose as the common period? Always the bigger value between the two possible periods, okay? Because period means the time to travel. If you traveled longer, then you will cover a more complete circuit or a more complete path on the XY plane, okay? That's why I choose the bigger value to use as our final period, the time to complete one cycle of the motion. So here I actually covered 2 cycles, okay? The first 4 solutions are these solutions. So the first value is just t equals to pi on 2 for x to be 0 and y to be 0. Very easy. Right. Finally, I want to express the distance traveled by the particle along the curve. So we want to use the arc length formula. The arc length formula, probably I should write my solutions here. The arc length is just t1, t2. Integrating your speed, not velocity. Here I used a very handy command again, norm. I'm taking the magnitude of the velocity, okay? So here you should have your speed function of time. And I'm going from 0 to pi over 6, which means my t1 is just 0, my t2 is pi over 6. And then I could write down square root of dt, which is 16 cosine squared 2t plus 9 sine squared t. Okay? That's it. And from my CAS calculator, I got a decimal approximation 1.80378, blah, blah, blah. Let's see the degree of accuracy. Correct to 3 decimal places, so 1.804. The unit is meters, okay? Right. Very easy. So we finished question 1. Now let's have a look at question 2. We start off by stating two complex numbers u and v, which are defined as u equal to -2 minus I and v equal to -4 minus 3i. And I want to express the relation absolute z minus u equal to absolute z minus v in the Cartesian form, where m and c are real numbers. Here comes my solutions. So the first line is z minus u, which is minus -2 minus I bracket, absolute value, equal to z minus -4 minus 3i bracket. And you should get z plus 2 plus I, absolute value, equal to z plus 4 plus 3i. Okay, my z is x plus yi, and absolute x plus yi plus 2 plus I, absolute value, equal to x plus yi plus 4 plus 3i. Now you can group them together like this. X plus 2 bracket plus y plus 1 bracket times I equal to x plus 4 bracket plus y plus 3i bracket. Okay, then you can just square this one plus square this one, not including I, as well as this one squared plus this one squared without I, okay? The approach I adopted is actually on CAS calculator, primarily substituting this z into the expression, and the CAS will directly give you the expanded form, including 2 square roots. Then you square both sides to get rid of the square roots. And finally, you solve that expression for y, because you expect a line, which is a perpendicular bisector between the 2 points, okay? So your final answer is y equals minus x minus 5, because you need to expand that to suit the specified form y equals m or mx plus c, okay? Like this. So I will just write the 2 square roots. You can just do 2 things in one line and say solve for y. Y is minus bracket x plus 5, and in that form mx plus c, y equals minus x minus 5, okay? Easy. Then you want to plot the points that represent u and v and the relation on the argon diagram below. So my u is minus 2 minus I, minus 2 minus I. So this is your u equal to minus 2 minus I, and the v is minus 4 minus 3i. 1, 2, 3, 4. 1, 2, 3. Okay, so here we have v equals to minus 4 minus 3i. Now, what is my relation? Remember, we need to realize that it's a perpendicular bisector between these 2 points, the perpendicular bisector of the line segment UV, okay? You expect something like this, and you also have your Cartesian equation with you, which is y equals minus x minus 5. So I need to use a blue line. I need to adjust that a little bit. Let me have a look. That's better. And I need to label that with y equals minus x minus 5, or we can just copy down absolute z minus u equal to absolute z minus b. So the geometrical interpretation, I would say, is very easy. Well, perpendicular bisector. Between the points z equals to u and z equals to v. Okay? Or you can say between the points minus 2, minus 1, and minus 4, minus 3, okay? Easy. And then I want to sketch the ray given by argument z minus u pi over on 4 on the argand diagram in part B. So, argument z minus 2 minus I equal to pi on 4. This is just the ray starting from minus 2, minus 1 excluded, okay? And this is my rotation angle, pi on 4, which is 45 degrees relative to the horizontal direction. Interestingly, here you already labeled the complex number u as a closed dot, but it will be excluded on my half line, which is to be drawn. The approach I would adapt here is that I can use an open circle outside the closed circle, then draw it in that way. For example, there we go. So this is my argument z minus u equal to pi on 4. And you could use dashed line to label this angle here, which is pi on 4, okay? If you don't mind, indicate here. Minus 2 minus I is excluded on the ray. Okay? Finished. And you want to write down the function that describes the ray, giving the rule in Cartesian form. So, we realize the gradient is 1 and the y-intercept is 1. And let's say y ray is x plus 1, where x is greater than minus 2, not greater than or equal to, because you want to exclude the starting point itself. Or you could say y subscript ray negative 2 to infinity restricted with codomain all real numbers. Y of ray of x is x plus 2 in function notation as learning math method. Right, finally, the points representing u and v and the minus 5i, I will name it as w. W equals to minus 5i. On the circle is given by absolute z minus z of c equal to r, where z of c is the center of the circle and r is the radius. So we want to find zc in the Cartesian form and find the radius r. Here is my approach. One possible method is that you can write down the general form, the standard form for any circle. X minus h squared, y minus k squared equal to r squared. And you realize there are 3 parameters you need to determine the values for. So I substitute x equals 0 and y equals minus 5. So I get the first equation in terms of r, h, and k. And then I substitute minus 2 and minus 1 into this relation, obtaining another equation. Finally, z equals minus 4 and y equals to minus 3. So x and y substituted, you get that equation. Finally, we can solve that system of 3 simultaneous equations with respect to h, k, and r. But notice, this could generate 2 pairs of solutions. So you need to include the radius is always greater than 0. Thus, getting rid of the unnecessary set of 3 solutions. Therefore, this is your final solution. And hk, this is your center. And z of c is minus 5 on 3, minus 10 on 3i, okay? And here is your radius. You need to answer the question specifically to its needs, okay? Another method, I think, yesterday I made a short video. I used a compass, which you guys might be interested in looking at. So let me explain my idea. If you have 3 points that determine a circle, you can find the perpendicular bisector of these 2 points like this, and the perpendicular bisector between another 2 points. The intersection, let me highlight these 2 perpendicular bisectors. The intersection between the 2 perpendicular bisectors will just be the center of the circle. And from here to here, from here to here, from here to here, all equidistant. Therefore, you can easily draw a circle through the 3 points, okay? Like this. So, you already have this one here, the first perpendicular bisector, and the other perpendicular bisector can be given by z minus u absolute value equal to absolute value z minus w, which is minus 5i as I defined before. The convenience of TINs by a calculator is that it can solve 2 equations over the complex domain directly. So I just put them in simultaneous equations form and solving for z, okay? Therefore, here is my center for the circle in Cartesian form. And also, you realize the distance between the center to any one of the point on the circle will give you the radius. So I just take the difference between the center and, for example, w. Then I take the magnitude of the difference, which will give us the radius, okay? So here is my solutions to all parts in question 2. Let's look at question 3. From the beginning, we've been given a specific function f of x, which is this guy here. And very first part, we want to find an expression for f dash of x and state the coordinates of the stationary points of f of x. Obviously, I actually sketch the graph first by creating a new problem on my document. And f1 of x is already sketched as shown in question 3c, okay? Which is this guy here. You can see it's upfront bolded font, which means it has been defined. Therefore, my derivative is that guy here. And then I solve that equation, this guy here equated to 0 for x, obtaining x equals to 0 and x equals to 2. Then I substitute the x values into f1 to get the y values. Finally, don't just state the x and y's, you need to state the coordinates. For example, 0, 0 and 2, 4 on e to the power of 2, or you can just say 4e minus 2, okay? Then, we want to find any asymptotes to their equations. The approach I adopted was limiting f of x by using x approaching to infinity. This is the only asymptote, which is a horizontal asymptote. Question 3c, you can just draw a graph like this. On this graph, I draw y equal to 0. This is my horizontal asymptote, and the shape was drawn with care. X-intercept as well as local minimum. 2 points of inflections, correct to 2 decimal places. And finally, the local maximum, 2 and approximately 0.54, correct to 2 decimal places. Okay? Make sure your graph goes through certain points with accurate positions, but you don't need to label them with coordinates. The position matters. For any sketching questions, I suppose you guys should realize on your CAS calculator, adjust the window settings according to the exam paper. Right. Very easy, 6 marks. Then, you've been given a family of functions with the unknown parameter n. Okay? This is just your parameter. N is any integers, which means 0 plus or minus 1 plus or minus 2 plus or minus 3, etc., etc. Then you want to find an expression for the g double dash x. So, here you can define your g of x as this, then take the second derivative. Actually, I should say this one is gn of x rather than gk of x. So, your double derivative, just copy down this expression here. But I suggest you write it as g double dash x equal to, okay? Then you want to find any non-zero values of x for which g double dash x equal to 0. So, on your CAS calculator, you realize it's non-zero, put in the domain restriction after your solve command. So you have 2 possible values, n minus square root of n and n plus square root of n, okay? These 2 values. The very last part of question 3 is you need to generalize from previous findings. So here is your table. You want to see how many points of inflections for specific values of n. Here is my approach. I firstly think of any negative integers until 0. By substituting these n values into here, I've drawn multiple diagrams, multiple functions, and I can see For example, if I pick and choose this bit, it's always in concaving down. And for this bit, it's always in concaving up. No point for change in concavity. So we don't have any point of inflection at all. I can say for n equal to 0, minus 1, minus 2, minus 3, minus 4, which means negative integers union 0. This is my number set. Then I put n equals 1 into the function and sketch the graph. I can see there is only 1 point of inflection. So for 1 point of inflection, oh, by the way, this should be 1 instead of 0, okay? I need to fix that later. Then for n equals to 2, 4, 6, 8, we can see the general shape always look like that. Here is 1 point of inflection, here is another point of inflection, depending on how big our n value is. So I can say it's just the all even numbers, okay? All even numbers. If you choose 3, 5, 7, 9, you will say, okay, the general shape look like that. 1 point of inflection, which is 0, second, and third. So your n values will be 2k plus 1, where k is any positive integers. But you can't say it's all odd numbers. If you say odd numbers, you should say all odd numbers excluding 1, okay? Because for n equals to 1, there is only 1 point of inflection. So we finished question 3, and let's move on to question 4. Question 4, big number of marks, but actually very easy. So you've been told the position vector for an aeroplane. And yes, it's describing the relative position to the origin, to the fixed origin. Displacement components are measured in meters and the time t is measured in seconds, where t is greater than or equal to 0. What's interesting in this year's exam too is that they didn't assess differential equation. Instead, they doubly assessed vector calculus. So that is an interesting thing to see, especially in these COVID-19 years. Okay, so we want to find the maximum speed of the aeroplane. Here is my approach. As well as question 1, I did some preparation work. I defined the functions like that. Then I defined my position vector function. First step, I just take the derivative for the velocity function. And then I use the norm to get the speed function. There are various approaches, but here are 2 common approaches. For any functions in specific form like that, a number, sine or cosine squared, plus another constant, then you need to realize sine something goes from -1 to 1. And if you square it, you will get from 0 to 1. These 2 are the lower bound and the upper bound. So if you want to maximize that guy here, you want to maximize the square root. To maximize the square root, you need to maximize the inner function, which means you can choose the biggest value of sine squared, which is 1. Here comes our maximum speed by substituting the whole thing with 1, okay? Alternatively, you could use f max for this expression here with respect to t, okay? The CAS will tell you which specific values we need to take for the value of t, and we can then substitute that value into our speed function to get the maximum speed. Of course, you could also draw a graph, but we need an exact answer to that question. So, final answer is 100 pi over 3 meters per second. Then you want to use R of A to show that the Cartesian equation of the path of the aeroplane is given by that relation here. So this is an ellipse, not a circle. I believe many of you have learned year 11 specialist math and learned the graphs of circle, ellipse, and hyperbole. So how should I derive this equation? First of all, I can state x is that guy here, which is the x component. Y is this guy here. The key idea is you want to use sine squared plus cosine squared equal to 1. And you want to isolate that guy and that guy. So you can minus 450 minus 400 and divide by minus 150 divided by minus 200 to isolate these two terms. Then stating these identity and substituting this one into here, substituting this one into here. So you can get, okay, x minus 450 over minus 150 squared, y minus 400 divided by minus 200 squared equal to 1. Expanding gives you the desired answer. So the second step is substituting and simplifying. For question 4bi, we want to sketch the path of the aeroplane. And we want to label the position of the aeroplane when t equals to 0 using coordinates and use an arrow to show the direction of motion of the aeroplane. Make sure you adjust your window settings like that. You press Menu, Graph Entry, Equation Template, and choose Centerform to sketch the ellipse. And also you can press Menu 4-1 to get the window settings and adjust the values according to the grid lines given on the exam paper. The x min is 0, max is 1400, x scale is how big the grid is. Y minimum is 0, Y maximum is 800, and 200 will be a desirable grid length in the vertical direction. Then I just entered the parameters into the ellipse template with K, H, A, and B. So here is my ellipse, but how could I determine its relative positions and the directions? On a separate page, I evaluated R of A 0. This is the starting position for 5200, which is here, the lowest point. And then you can say, okay, 0 to 12, how could I know that? Because if you look at the period, these two are the same angle. So the period is just 2 pi over pi on 6, which is 12. We know it's more likely a circular or elliptical path. It's just one cycle. We can break that one cycle into 4 sections. Starting from 0, then we can say, okay, when t equals 3, this is the coordinate. So from here to here, then here, t equals 9, here, and then t equals 12. Returned to the original position. That is one cycle, okay? So that's how I determined my direction of motion for the parametric equations. Right, make sure we label the starting point and also indicate the directions, but you only need one arrow, not 4 arrows, okay? I overly down that question, giving too much information. Okay, question 4c. We've been given another jet-powered drone to make photographs of the air show. So here is the position vector of the flying drone. Okay, looks like a projectile motion, and we want to sketch the path of the drone on the axis provided in part B. Second, using coordinates, label the points where the path of the drone crosses the path of the aeroplane, correct to the nearest emitter. Right. My approach was solving x equals to 30t, y equals to minus t squared plus 40t for t and y. Then this is my Cartesian equation without any t. Or you could just solve for t first, then substitute t into your y function. And finally, you get your Cartesian equation like that. Notice that these two are the same thing, but it will be easier to draw that because you can realize its x-intercepts, 0 and 1,200. But how could we further find our intersections? We just put this and the Cartesian equation of the plane together for x and y. There are actually two sets of solutions. So you want to round this value and this value to the nearest integers, which is 316. And the y is 310. Roughly here and here. 600, 400, exactly. The turning point. And finally, you better label 0, 0 and 1200, 0. Starting from here, ended here. In that direction, okay? Okay, so last part. We need to justify and determine whether the drone will make contact with the aeroplane. This is typically the collision problem in vector calculus. So the idea is you equate your x component of the aeroplane with 30t, which is the drone's x component, and solve that equation. This is important because the common domain is 0 to 40. You need to specify that. From that equation, we obtain a t value. Similar approach for equating the y functions, y component, and solving this equation over 0 to 40. We should get 4 solutions, but the final solution is 26 something I couldn't remember, but you can see this t value is no same to the 4 values, totally different, which means there is no t value for the x coordinate and the y coordinates to be the same. So the drone and the aeroplane will never collide, which means they will never make contact with each other. Right, question 4 finished. Question 5. For the first part, you want to mark all forces that act on each object once the object on the platform has been released and the system is in motion. Actually, at the beginning, I was a little bit confused because the question described 2 possible forces, actually 2 horizontal forces opposing the motion of magnitude F1. And another horizontal force opposing the direction of motion of magnitude F2. F1 is for the section AB, F2 is for the section BC, and B is in the middle point. Initially, I've drawn another M representing here to here, okay? The motion from here to here, but actually I realized there's no need to doing so. So I just need to say, okay, this is mg. This is my reaction force, N, let's say Nm, okay? Tension, gravitational force mg. Another tension, and finally, the direction of the motion should be in this direction, accelerating towards the right direction. And here comes our opposing force, F1. Then you could say, okay, my F1 is given by K times mg. In fact, K is just a commonly known terminology, coefficient of friction, because mg is my reaction force. We have a formula F equals mu n. So this is just my sliding friction, okay? But it's not clearly, explicitly stipulated in the specialist math study design. I believe if you are using Cambridge textbook, you will still cover the idea of small f equals to mu mg or mu n, the sliding friction. However, in the current study design, they have to scaffold you in an informative way, giving you ideas. Okay, opposing forces, opposing to the negative direction, and it's proportional to the mg. Another case, if it's on the inclined plane, it's not mu times mg, it's actually mu times mg cosine theta, okay? Anyway, we want to show an expression for the acceleration in meters per squared second of an object on the platform in terms of k as it moves from A to B. So we only consider F1 for this stage. With the given diagram, we know it's moving to this direction, and this is my driving force, retardation force, driving force again, retardation force. So my total equation for the motion will be F net equal to m plus m. We combine these two masses together, times A equal to mg minus t plus t minus F1. Simplify it a bit further, 2ma equals to mg minus kmg, which is F1 here. And you take out the common factor mg, you get 2ma equals to mg 1 minus k. 2a is g times 1 minus k, and therefore a is half g 1 minus k. That's it. But this is a 2 marks question, so you better write down the equation or 2 individual equations of motion, then show all the working out. The next part, the system will only be in motion for certain values of k. Find these values of k. There is a very small detail but important. K is positive real numbers, which means k is greater than 0. You have to specify that. If it's in motion, the acceleration will be either 0 or positive. Given an initial push, if you are pushing something, only push it, it will have an initial velocity and start moving. Once all forces on the object is 0, it could be moving at constant acceleration. But what's important here is that the object on the platform is initially at point A. Okay, initially at point A. Actually, I should look at a specific term. If it's starting from rest, to be safer, I would say the acceleration is just greater than 0. In the previous study design, not the current study design of specialist math, there was once an idea of limiting equilibrium. In this case, this involves the limiting friction. You could also argue that A is greater than or equal to 0, considering the object is on the point of moving to the right direction. So you could have 0 smaller than k, smaller than or equal to 1, okay? But in this case, I would just say 0 smaller than k, smaller than 1, okay? So, shouldn't be a big problem. Then we move on to the next question. Point B is midway between A and C, so halfway through, which means 5 meters. Find in terms of k the time taken for the object on the platform to reach point B. So we want to cover a displacement of 5 meters. Therefore, I will just write down UVSTA, the SUVAT stuff, and substitute the A value, the A expression from previous part. U is 0, T is unknown, but S is 5. So you get that equation and solve for T with K domain restriction as well. And finally, this ugly expression can be treated as our final answer, but it could be tidied up. For example, 2 square root of 5 divided by g 1 minus k. You take the minus into account and swap the order of k minus 1, okay? Alternatively, you could also substitute g here. The value of g is 9.8 at the beginning. You should be able to get that expression here. Of course, you could tidy this expression up and having t equals to 10 over 7 root 1 minus k, okay? Next thing, express in terms of k the speed vb in meters per second of the object on the platform when it reaches point B. So you want to use the formula v equal to u plus at with initial velocity 0. You know a is the expression derived in part B, and the time above is just the total time to travel from A to B. So you multiply this one with the acceleration together, you get that expression. And if you want to tidy it up, you could also get that answer. Of course, you could also leave your answer in terms of g and k as well, because g is a commonly acceptable expression for 9.8, the gravitational acceleration. Finally, when the object is on the platform at point B, the spring breaks. The velocity of the object at point B is vb equal to 2.5 meters per second. So this is a new stage. Let's say x is 0 and v is 2.5. The force that opposes the motion from point B to point C is that force here, okay? It's no more just k times mg. It must take the air resistance into consideration, where v is the velocity of the object when it is at distance of x meters from point B. Right, so this is actually giving you a hint. We are using a new stage. The object on the platform comes to rest before point C. Find the object's distance from point C where it comes to rest. So we want to find the distance from the current point to point C, which means I want to use 5 minus the x to get the final distance. Looks like we want to solve some sort of differential equation. Because the rope is broken, we must get rid of t, okay? So the total force, m times a, is 0 minus the whole retardation force, which has 2 parts. You can use your CAS to simplify that problem to get a equals to minus 16b plus 3g over 40. This problem is related to v and x, so we don't want to use dv dt. Instead, we want to use v dv dx to represent the acceleration. How do I translate v dv dx on our CAS calculator? We could say, okay, v times v dash. So v dash means dv dx. And my independent variable is x, dependent variable is v. Using dsolve will give you a relation between v and x. With this known relation between v and x, you can substitute v equals 0 to solve for the value of x. But remember, your point B is here, your point C is here. It stopped somewhere in between B and C. And this is the distance we want to find, okay? This is the place where it stops. So, make a link between this number here and D. We want to use 5 to take away this number. So the distance between the stopping point to C, let's say S to T. S to C has distance of that. Correct to 2 decimal places, 3.15, okay? Another method will be using separation of variables. Of course, you need to use VDX as well, but it will take you a bit longer because you want to flip them around, divide V through, and also making dV your integration variable. And strategically, I've chosen 0 to 5 minus d as reasoned above, and the starting velocity is 2.5. Stopping velocity is 0. So on the right hand side, I'm integrating from 2.5 to 0, and from left hand side, I'm integrating from 0 to 5 minus d, okay? Once you stated your new equation of motion, carrying out all process for separation of variables with the correct integral equation, you can just throw the whole thing into your CAS calculator and your CAS will give you an elegant answer directly. Finally, you can just solve for the unknown distance d, which is desired by the question, and the answer is the same as in method 1, 3.15. Okay? So, question 5 finished, and our exam 2 explanation and suggestion finished. Finally, I need to make this disclaimer, as always. This suggested solution is not intended to be an exemplary guide, and it is in no way endorsed by or related to VCAA official opinions. This is just the author's, which is me, personal opinion for non-profit pedagogical uses only. Teachers and students are suggested to refer to the forthcoming assessors report for 2020 exams in 2021. VCAA retains all copyrights to the exam materials. Right. I think this video in future will help some forthcoming students during the specialist math course, for example, 2021. And I hope you guys could find this video helpful in some way. Best of the luck and all the best wishes for the 2020 VCE students who are doing specialist math as well as other math subjects. Thanks for watching, and I'll see you guys all next time. Bye bye.